Dr. David Kaiser, Dave Kaiser. I am, am I saying, is Kaiser? Is that correct?
Yeah, yeah.
Okay, awesome. I am so excited to be talking to you today, and I'm so happy that you're here. How are you?
I'm good. I'm good, thanks. How are you doing?
I am wonderful. Wonderful. I've recently, the last couple of episodes that I've recorded, I've been very fortunate because I've talked to people who seem to have their perspective cross disciplines.
Hmm,
So I spoke to, for example, a marine biologist who's a musician,
hmm.
and there's a ton connected between, for example, acoustics and the underwater world. And
Right.
we're talking about, in particular, for example, how dolphins uh, they see things visually, but they also see with their echolocation, and so there's almost like several dimensions of their ability to process things and perceive things,
Right.
which was super cool, and the impacts that has on reality, and when also the limitations of our perceptions that we can only see. Imagine how cool it would be if we could see with echolocation, and the amount of more richness and depth and the discoveries you can make if we're able to kind of just even open up that lens a little bit more
Hmm.
than what we have right now. And you wear a lot of hats too. You wear a philosophy hat, you wear a historian hat, you wear a science hat.
Hmm.
Um, and I want to hear a little bit about the background. But one thing I really wanted to ask you, perhaps maybe to kind of drive the direction of the conversation,
Right.
is I've noticed in your book, How the Hippies Saved Physics,
Hmm.
that when it comes to history, you're very, very even keeled and present both sides
Hmm.
of everyone's perspective almost every time that you write about something, no matter um, how colorful the character may be or not.
Right.
You generally present their side and then the opposing side, and you're very fair about that.
Hmm.
Um, how do you approach science the same way? How do you approach do you wear or is that two different hats that you put on? That science, you need to find one way that's the right way, and then history, you kind of, okay, well, I can kind of see that how this could be the case or that could be the case.
That's a really interesting question. I guess I've never thought about it in those terms before, but I think there are similarities. Now that you say it, I can sort of recognize it as you mentioned it. Even in the sciences, we're certainly trying to be correct. That's a fair, that shouldn't be a controversial statement. But I think one thing that I find helpful as an historian as well, or just someone who's interested in how we've gotten to where we are, as a community, that we're going to be wrong just all the time, and we have to be okay with that too. We're going to learn from that. Hopefully, we'll be able to learn from that. So even in my work, when I wear my physicist's cap, and I'm trying very hard to check every factor of two and minus one and all that careful stuff, we, my students and I, my gang and I, certainly want to be careful and correct.
Mhm.
But by virtue of being people in a given time and place, we're going to make mistakes. Hopefully, some of those will be what I like to think of as kind of productive mistakes that will
Mhm.
be wrong. We'll be
Mhm.
wrong a lot, but will we be wrong in ways that are juicy enough that we or other colleagues or some people in the future, or whatever it might be, can kind of figure out where we went wrong, and by doing so, give a kind of course correction. And I see that happen just over and over and over again when I then put my historian's cap on,
Mhm.
and look back at recent history, at more distant, history of science. And I think that's kind of a great thing. That's not something to be kind of, worried about. And so I get maybe that's what informs my historical work as well. The folks I've been writing about in the hippies book, which I look forward to chatting about, my other historical work. I've been writing about some people who are still well known in the sciences. Albert
Mhm.
Einstein, people have heard of him. Richard Feynman, sometimes people who are less well known, I think, still did really cool things and substantial things. And isn't it worth spending some time with their work as well? And each of them, Einstein as much as the other folks, have been wrong much more than they were right from our current perspective. What we've come to learn in the years since. And that's not throwing shade, like, that's how it's gonna be. And
Mhm.
so I guess I do, therefore, now that you say it, try to be, what, you said even keeled. I just wanna treat these folks with respect, because I think what they were doing, they really cared about, at least in the
Yeah.
instance that I and that catch my attention, my
Mhm.
imagination. They were being earnest, sometimes they were being very having fun, that's not a bad thing either. They were clearly trying their best, and the fact that today I might think that they didn't understand this thing that maybe my students and I think we understand better, that's a good thing too.
Yeah.
So I guess there's no harm in saying these folks were 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 trying to think creatively from where they were,
Yeah.
and we as a community can benefit from that, even if we if the picture looks a bit different today.
Sure. Yeah. And there's the I guess a very cool and color and maybe specific example, and I want to kind of get into the technical aspect of this a little bit later, but the double slit experiment that you
Yeah,
write about in your book seems to have generations, like a next gen version of the experiment, a next gen version experiment, and every single time it's built on the shoulders of enormous respect and reverence for the original scientist, but not to say you're an institution and what you're saying has no has, that's the top of where you can possibly get.
yeah,
Rather, you broke the ground for us, and now that we have all these new tools and we have these new tools in our tool belt, what can we tinker with? How can we build? What can we have fun with? And
yeah.
so it's not to and I think that the common theme of a lot of these scientists that tend to either be groundbreaking or embrace this is that they keep their minds open enough to able to see to see that they're just we're all just at a point in time. That's all we are. And,
Yeah.
and it's not an insult to us to say that at another point in time the variables might be different and the context might be different,
Mhm.
and it's nothing to do with me, nothing to do with my train of thought, nothing to do with my experiment. It's just this is just a different world now, and now we understand things differently.
That's right, and our goal can be to contribute to that
Right.
longer term process, right?
Right.
We're not gonna
Right.
win. It's not something where the game ends and there's a winner. I hope it won't be like that. But we say, we really contributed with some careful, hard thinking, hopefully some real satisfaction, even some fun as well.
Yeah. And do you? I mean, I imagine you take this probably similar approach to philosophy or with your philosophical perspective on things. So generally, you have evidence until the evidence runs out, or there's something else that points to the contrary.
I guess so. I should say I'm certainly not trained as a philosopher. I have many friends who are, so I know enough of what they do to know I don't do it because
Okay, that's fine.
with great respect. I mean, that's his own real discipline,
Hmm.
and I know enough to admire parts and to certainly benefit from and try to bring some of those insights into my own work, both as an historian and as a physicist. Um, but I think even there, I mean, the the really juicy philosophical questions tend not to have like that's the answer, right? If that were the case, then we would maybe be done with Plato, and we're not done with Plato or Immanuel Kant or name your favorite before or since. And so again, I think that does foster respect for the clarity of the argument, and I think that's something that we can strive for in
Hmm.
all of our work, not just if we are being philosophers. The clarity argument, the strength of the evidence, and then put our best case forward. While again, as you say, let's not make straw men. Let's not try to kind of pull a shortcut to make a different side look weaker than the position might be. Let's give it the best shot. I think that's that sounds very vague, I guess, but I think that's something that can be valuable well beyond just philosophy.
Sure, sure, certainly. So, what what piqued your interest, unless it's just a matter of fun, about a controversial topic, a controversial cover, which I loved, by the way. I went home this past, I went to my parents' house this past weekend. I'm the oldest of six, and I come from an Orthodox Jewish family. My mom is very protective, and she took the cover right off the book. I kept it lying around on purpose just to see her reaction. And she was like, "I love that you're reading this. I love the material. I don't want my 13-year-old son hanging out at the cover." And I laughed. I did it on purpose, but so were you afraid of pushback? What was your
Yeah.
perspective going into this, and how'd you approach this? Because again, it's relatively niche, and I feel like, I mean, especially from your background is top tier as far as institution and reputation goes. So would this be considered like a little treading dangerous waters for you?
That's a great question as well. First of all, I love the story about your mother and the book cover. That's like fantastic.
Yeah,
Can I
yeah.
warm up to that? So I didn't have any say over the cover. I guess I had veto power, but the press gave me the covers like, oh, it took me a while to
I
see.
loved it.
And then my favorite variation on that, I just briefly say, first of all, I'm very honored. The book was translated into Italian and a couple of other languages. And years later, I was in Italy and I saw in the bookshelf a second printing of the Italian edition. I don't read Italian. It was just like super cool.
Mhm.
And I don't know if if your listeners will know, the standard edition of the cover that your mother got so upset about shows a naked man doing a headstand in the forest, presumably lost in thought. Now, because it's being sold to us, puritanical Americans. Um, they put the publisher I thought very creatively, put a picture of like a model of the atom centered so that there's a colored dot covering the guy's, butt. And so it's not actually fully a naked picture. It's been doctored with signs of the atom and quantum physics. I thought it was actually pretty playful.
Yeah,
No,
I loved it.
I thought came out. I mean, again, I got used to it after first being a little surprised, and so I'm in Rome years later, and in the second Italian printing, they left off the atom, meaning they really just showed the naked guy on the cover. That's Rome, like that made perfect sense there too. Anyway, as an aside about
Yeah, it's very
um,
fitting.
but indeed, so I really I was hooked on this material when I kind of stumbled it. I knew little bits of it from even when I was an undergraduate, not the particulars about this group of people, but some of the big ideas, which we'll talk about, quantum entanglement and these big, you know, really delicious debates over quantum theory and how can the world work. Has been a long term interest of mine,
Hmm.
intensely. And then I started learning about this group that called themselves the Fundamental Physics Group, based in the San Francisco Bay Area, mostly in the 1970s. And I learned more and more, and they were indeed colorful. They were very well trained. They themselves had received PhDs, almost all of them, from very, very, top-notch departments of physics across the country. They were very well trained, and they were, you know, working in a time of great change intellectually, culturally, institutionally, politically. They were kind of caught in a real moment of transition for the country, even beyond the United States. And I found them fascinating as examples of what happens to people, to smart, earnest, well-trained people when the rules change, the rules of how
Hmm.
you make a career in the sciences, what it's like to be a researcher. How do you fund research? I mean, questions that are on many of our minds again today. It's not the
Yeah.
same, but a period certainly of rapid change, right? And so these were people who really impressed me because they were doing the best they could under sometimes quite unusual and sometimes difficult circumstances. And they didn't stop pushing and didn't stop asking good, hard questions. The answers that many came up with might not stand the test of time, but as we said a moment ago, that's kind of how it's always going to be, I think, or at least we should expect that.
Hmm.
And more often than not, they seem to really also be having a good time under not always easy circumstances. They really made something out of these deep, enduring questions. To my mind, some of their other enthusiasms aren't my enthusiasms, and that's okay too. You know what I
Yeah.
mean? So I had, nonetheless, I wanted to be extremely careful in doing the work. Some members of that group have written a lot about their experiences to this day, which is very helpful to me. I should say they were, at the time I was writing, they were all alive. The main
Hmm.
course said, older than me. They were active at a time, I mean, largely before I was born or just when I was a little kid. So they're older, but at the time I was working on the book, they were alive. I should say they were very generous with their time. I mean, lots of making time for me to talk with them, formal interviews, informally, follow up by email. I mean, they were really very generous, and I still appreciate that as well. Um, where am I going with that? And so anyway, the idea was these weren't typically household names. One or two of them were reasonably well known, even to my colleagues today in say physics.
Hmm.
But a lot of them weren't, and a lot of their activities, you might say antics, were off the beaten path, and that actually drew me to their story. That was part of the what I wanted to learn more about.
Sure.
How could people ask interesting, hard questions in settings that didn't look like the universities I'd been trained in, or even the universities that they had been trained in, for that matter,
Hmm.
earlier in their own careers. Um, so, I guess I'm just saying that they were. I was really interested in what does it take to try to ask juicy, hard questions about how the world works.
Yeah.
Some of the basic laws of physics that were not so straightforward or so easy to make sense of. They're still not, actually. While doing so, kind of wrong-footed compared to the kinds of careers that they themselves had expected or trained for.
Right.
And then just part of the story is that they were basically finishing their formal training, their PhDs, in the late 1960s or early 1970s, just when a wave of really, really significant budget cuts hit the field. Lots of change, not many jobs, at least in for
Sure.
PhD trained physicists. It was a huge glut on the market, not just for universities, but also for government labs, for industrial labs, just the whole job market for PhDs in physics and some other areas in the sciences, it really collapsed and
Hmm.
collapsed more ferociously, more quickly than had ever happened in American history for that kind of section of the job market. That was interesting to me as an historian. What's it like to try to make your way, asking hard questions about quantum physics, about entanglement, in their case, about even wider, further flung things, without having the kind of stable perch that they might
Yeah.
have expected to be able to do that from. They had, as I say, they did PhDs at very fancy elite departments. They published in the peer-reviewed literature. They were doing the right things.
Hmm.
And I would say the only miscalculation they made was graduating when the bottom fell out of the market. So they had to scramble, and they were often very creative. Frankly, today we'd call them entrepreneurial. They made it work,
Sure.
which was
Right.
pretty impressive in its own right. Um, and
Fundamental
so
physics group may as well be like a San Francisco startup today.
I
That's
mean,
that's kind of feel that it has.
it really would have been, and in fact, it's not so far off. As I have learned from other historians' work who've been digging into that as well. A lot of what we now call Silicon Valley was starting out in similar circumstances in people's garages in that time period. It
Hmm.
was a kind of hippie counterculture scene for what would grow into the personal computer industry, what would have really, I think, really interesting impacts in how we understand quantum physics, and how it does or does not relate to relativity. So they were actually rubbing kind of shoulder to shoulder there. That's right.
Sure. So there's so many good follow-up questions.
Mhm.
um, when you're putting your historian hat on and you're looking at this time frame and the zeitgeist of the world at that point, I would imagine that on one hand, it's got to be in America, or at least American interest,
Mhm.
to understand these big questions,
Mm.
right? Of how the world works and all this kind of stuff.
Yeah.
Um, why do you think, looking back at that point in time, culturally and historically and politically and socially,
Mhm.
do you think the bottom fell out?
Yeah.
And it would be in, especially because this is around the time of the Cold War, and
Yeah.
there's intense competition with all sciences, between
Yeah.
America and the Soviet Union.
Right.
It would be shocking to me that you just pull away from something so big as all these big questions that they're asking,
Yeah.
unless you just don't want it to be being done in the public domain. Um, Potentially, I don't. I just thought of that as I was speaking, but I don't.
Yeah.
But what do you think?
Well, it's a great question. That was what also attracted me to this material. Again, wearing my sort of historian's cap, is what I think you can mind is that the Cold War had several phases. It wasn't just one unbroken thing, which made more sense to me the more I looked into this episode and other things I've written about, as an historian as well. And so, in fact, that's part of what caught this group and frankly a whole generation by surprise when there was such a rapid reversal of fortunes. So, as you and I'm sure many listeners will know, the relationship between science and the U.S. federal government changed in a huge, huge way during the Second World War. And that was the era of massive projects for defense, for the military, that involved all kinds of really genuinely cutting edge physics and related engineering, chemistry, metallurgy, really many, many fields, the social sciences and linguistics as well, for that matter.
Mhm.
And I mean things like the Manhattan Project, right?
Yeah.
The very, very harried effort to create nuclear weapons from scratch. I mean, it was in an incredibly short amount of time. And that involved some very basic nuclear physics, some very hard things in electronics, and what we now call chemical engineering. It was really complicated and involved more than 125,000 people across North America in a highly
Wow.
top secret effort. Huge, big, big scale, billions of dollars. I mean, really a lot. Likewise, the radar effort, which was headquartered largely at MIT, where I teach, that was also just a massive effort, huge laboratory, tons of specialists across the board, and really had an enormous impact on the direction of the war. So, coming out of the end of the Second World War, the U.S. federal government said that was actually pretty helpful. Let's continue this relationship with universities, with a whole new expanded series of government laboratories they were then building at a rapid pace, industrial laboratories building up as well across the
Mhm.
United States.
Yeah.
And so the federal government continued to be the biggest patron, the largest payer for basic open-end research, as well as more kind of oriented things applied things that could be useful for this or that weapon system. So that by the early 1950s, nearly every physics student in the United States, at say the PhD level, and faculty and so on, was being supported one way or the other by the US federal government.
Right.
Most of them were not doing weapons work. It was not Manhattan Project per se. That was a small number of people after the war, but the field was being supported. And from the government's point of view, this seemed like a great bargain for many years. The idea was keep these extremely smart people trained at the best way they could ever be trained in case this new Cold War with the Soviet Union ever turned into open warfare. There was a great worry that it was hard to staff the Manhattan Project and the radar projects. People didn't know where were the trained people. Were they, they weren't like on the government, kind of payroll yet in the late 30s, early 40s. So in the 50s, late 40s and 50s, a lot of these government advisors and policymakers say, let's make an entire generation, let's make multiple generations of people trained at the highest level, have them trained to do whatever their curiosity demands, which is kind of extraordinary looking back. And then if we ever need them to pivot, we'll know where they are and we can have confidence in their skills. And
It's
that's
amazing, by the way. And
amazing.
I feel like that's an awesome strategy because what you're essentially saying is we don't know what the future is going to need, so let's just nurture all sorts of scientists.
I think that's exactly right. And again, it was a lot of the people who were the so-called program officers, the people at the federal agencies. These were mostly military defense agencies.
Yeah.
The National Science Foundation, which is all civilian, was founded in 1950. Its budget in those years was just a pittance compared to Office of Naval Research, what became known
Sure.
as Atomic Energy Commission. And yet, even at those places whose main job was defense, was military preparedness and so on, oftentimes, just as you say, the people in charge of dispersing money said, what's going to get the largest number of really well-trained people? And they talked about them as a so-called standing army of PhDs in physics.
Mhm.
These were a commodity to be rationed and controlled as if it was like gasoline during the war.
Mhm.
We need more and more of this precious commodity, really smart, trained scientists, often including physicists and allied areas. So what happened is that led to an enormous expansion of U.S. universities. It led to expansion of many fields of study, not just physics. Physics happened to grow fastest during this period of growth, but every field grew exponentially quickly in terms of enrollments, in terms of budgets. Lots of people entering higher education who might never have had the chance before. The GI Bill helped a lot for that too. So
Yeah.
not everyone, it turns out, but many veterans qualified then to have their higher education paid for, including both undergraduate and graduate study. It was an amazing system. I think it honestly remade the country. And looking back, I'd say in many ways for the better, in ways that I think we should be proud of. Wasn't perfect, right? If I had a magic wand, I would have changed things about that too.
Yeah.
But it was a remarkably effective program. And, it didn't last forever, as we know. It really starts to falter. That's what sets up the hippies book and other historical work. It starts to falter with the kind of years into the slog of the Vietnam War, meaning the late 1960s into the early 1970s. That
Mm.
sets up what I was writing about for this book. And there were several reasons that came together to change this kind of consensus pretty rapidly. On the one hand, auditors, like the finance people within the U.S. military establishment and the Pentagon, were doing their own internal audits as well. What's the return on investment for the military's main job, which is military preparedness, on spending very generously on open-ended basic curiosity-driven research? That's they should ask that. That's not
Yeah.
a wrong question for them to have asked
Those gosh darn
at that
auditors,
time.
right?
Especially when the newest war, when the Vietnam War was absorbing many resources, many more
Right.
that had been kind of expected early on. So they really have to worry about making ends meet, and they conclude internally, this is not we're not getting the right return on investment. They conclude. Other groups contested that again. All these economic models, you could find different ways to interpret them, but that was the official internal conclusion.
Mhm.
A preliminary report in 1966, their final report in 1969. That's just when we're going to start seeing these changes, right? That, as you might know, coincides with a real explosion of concern about this heavy role of the military on U.S. campuses at the height of the Vietnam War.
Right.
College kids
Massive distrust.
about trust. undergraduate students losing their draft deferments because the military needed more and more so-called boots on the ground. The war was going, frankly, not well.
Hmm.
So people used to get deferments if they were a full-time student, and for other reasons, those deferments no longer get given. A few years later, they're taken away for full-time PhD students. There's a desperation for changing the system.
Hmm.
Um, and that has, quite understandably, lots and lots of people on US campuses and elsewhere very, very concerned. Why is the Pentagon playing such a large role, both funding all this tremendous amount of research and now having say over who can even stay in their studies? So that leads to these, very famous campus protests against the escalation of fighting in Vietnam. And so you have from, so to speak, from without and within, lots of people saying by, let's say, 1968, 69, 1970, this system that seems so obvious coming out of 1945, it needs to be really, reconsidered. Combine that with what would soon come as these oil shocks and just economic downturn. It was tough. All these
Yeah.
things lined up within a very short window. And so funding had nowhere to go but down. Funding for the natural sciences fell like a stone, and none fell faster than physics because partly it had risen quickest.
Right.
So that's the setup for when these folks I wound up writing about were just finishing their PhDs, looking for the kinds of jobs they had been led to expect. They entered grad school in the years after the Soviets had launched Sputnik, which is a great kind of shock to the system. Released even more. Frankly, very generous funding for the sciences and for universities in the US. So from the late 50s into the late 60s, it was really boom times. And that's when this generation went in. They were being told, we'll pay for all of your school. You'll have basically you'll have a guaranteed job afterwards because we need more and more people in these spots. And it was just a complete like rug pulled out from under them from that generation, not just these folks, with this series of reversals, such that, as I write about in the book, by the late 1960s, by around 1968, there were more people with PhDs in physics looking for jobs than jobs on offer for the first time in really in this whole
Wow.
system. And then by 1971, the ratio dropped to 20 times more applicants than jobs. That's
Wow.
not good if you're finishing a PhD looking to, get a job and build the next stage of your life. It just fell like a stone. And so, as I say, that really captivated me as an historian. What's it like to try to ask questions about how the world works when so much is changing, as you say, culturally, politically, in terms of just budget and resources, the types of careers you could expect to have, real change. And yet it's not that science stopped. Some of these folks carved out a pretty creative, kind of different path.
Hmm.
It had some recognizable elements. They had done PhDs. As I said, they were using their skills, I think, very creatively, but they weren't, kind of becoming tenure track professors for the most part, who could look forward to a kind of 30 to 40-year stable career. It was really at sea.
Yeah. Yeah. And what's also interesting, I happen to love that time period. I'm absolutely fascinated by the 50s, 60s, 70s, that whole movement. And like, it felt like America was rebirthed almost at that point in time, and rebirthed into different little sects almost of like the
Mhm.
country, which is really, really interesting. And I love this whole like hippie movement. But one thing that coincides directly with this same time period is a massive level of distrust
Yeah.
in the hippie mentality. You got the Manson, murders, and you have, the post Summer of Love. You have the concert at Monterey where with the Hell's Angel that killed that guy at the Rolling Stones concert, and the general people weren't hitchhiking anymore. It wasn't free love everywhere.
Mhm.
What you call potentially darker drugs were making their way
Mhm.
to San Francisco relative to the LSD and mushrooms, and free love was
Yeah.
more speed and heroin and amphetamines and stuff like that. And so you kind of had this at the same time as this funding is collapsing,
Mhm.
the actual mentality that a lot of these people were building their premise on were getting was getting really knocked down in the American perception. And so these people not only had to deal with the cut in funding, they had to deal with the fact that people didn't trust them as a whole because of the way they looked or the way they dressed or the way they behaved. I mean, that's clear, right?
I think that's right. And so, famously, even before then, when Ronald Reagan was running for governor of California, long before he
Mhm.
became president of the United States, he had this famous quip. I'll probably get it wrong. You might know it. It says, how do you tell a hippie? Oh, what was it? They have, oh, I'm not going to get it right, but they have hair like Tarzan. They dress like Jane. They smell like, they're They're 8. He was just being, and that played to the base, right? That played to certain
Sure.
people who, as you say, were watching on the nightly news some of these anti-war protests, or just the more exuberant expressions, let's say, of a kind of really kind of enclave, almost like a closed society, almost a kind of the Bay Area hippie life. Wasn't for everyone. It wasn't that everyone loved it, and it started inspiring, as you say, a kind of backlash as well. Yeah, and so it was not everyone on the same bandwagon by any means.
No, far
Yeah.
from it. What does it make you think about when, and I don't know if you'd call this a reemergence, but gentlemen like Hal Puthoff has been popping back into mainstream, and what's really interesting to me is that I think he was I think it was Hal that's been making the rounds on different podcasts and TV shows and big news stations talking about these things these programs that he was part of. And what's funny to me, or that I think, is that everyone that everyone was discrediting him, in the past for being crazy. And, all these things do tend to lean towards typically what we would call mystical or a little bit more, not, not grounded, a little bit less grounded, I would say.
Mhm.
And he didn't even change, like, there's not even a change of the face of the movement. Like, it's the same guy for this entire period of
Mhm.
time. It feels like
Right.
history is bleeding into the present right now. And you have a lot of and listen, like you mentioned, a lot of the characters in the story are dead now, unfortunately, but a
With them,
couple are still alive, and the ones that are still alive are starting to make some more noise now. Is this because there's been advancements, you think, or do you think that it's become more palatable? What do you think is and I know there's speculation, so if you don't wanna speculate too much, I
yeah.
totally understand, but it's up but what do you think about this?
Well, it's really interesting. So again, Hal Puthoff is someone I did write about a bit in the book. He wasn't one of the main circle, but he interacted a lot
Sure.
with the folks I was writing about. They certainly knew each other then, and many of them seem to be still in touch regularly now. So Puthoff, again, he was trained. If I remember correctly, Puthoff's PhD was from Stanford. He taught for years at Stanford in basically quantum physics, quantum electronics, lasers, and
Mhm.
things like that. He worked for years at a Stanford-affiliated research lab that then was spun off to be independent, called SRI, Stanford Research
Research
Incorporated, I think
Institute.
it was.
Yep.
SRI. Um, and so again, he's like these other folks I mentioned, impeccably well trained. And then he had, a broader set of interests than was typical. And I don't say,
Mhm.
and that's not a bad, to my mind, that's a good thing. I mean,
Yeah.
that's okay. And so Puthoff was among the first to do things like subject the Israeli magician turned, kind of ESP
Mr. Uri Geller, right.
Uri Geller. So Geller was, doing club shows in Tel Aviv in the early 70s. And then he began to say that he actually had genuine, ESP-like powers and not just clever kind of sleight of hand. As I like to say, if the year is 1972 and you say you have genuine ESP, one thing will happen to you. You'll be whisked on a plane to San Francisco, which indeed more or less happened. To the States was in just this time period, and subjected to hours and hours of scientific scrutiny and test by people like Hal Puthoff at this SRI spinoff place. They published articles in Nature, or one of the leading scientific journals on the planet, about their findings.
Mhm.
That's not the last word, and it's still controversial, and, but the point is Puthoff was placed in some sense better than most of the folks I was writing about, better in terms of the traditional kind of resources for scientific investigation. And he was really interested in the nature of consciousness. He was interested in, well, are there overlaps between what we understand in quantum physics and these other questions that sometimes fell outside the typical, kind of boundaries of physics.
Mhm.
Um, I think in more recent years, he, like other folks I was writing about, have gotten interested or reinterested in things like UFOs and exotic ideas for space travel. And so I don't know the details. My sense is that why some of these folks, we might be hearing more from them now, is a couple of reasons. First of all, UFOs are a topic that keep on giving, right? That's fascinating for lots of people kind of now, and
I'm having a lot of fun with it. For sure.
and as you know, there's, more and more, I guess I'd say, moves toward disclosures from U.S. federal sources that maybe once were really kept highly confidential. Now there's at least some more public discussion. It's, again, I'd say it's, still rather controversial, and I don't know the answers and all that, but it's in the news. I mean, the point is, it's a topic that will be covered now from venues like the New York Times and not only kind of non-mainstream outfits. Another thing that happened in between is the internet. And so it's a lot easier, for good and not always for good, but it's a lot easier to get one's message out there without having only to go through the gatekeepers like the New York Times. I think you throw
Mhm.
all those things together, and it makes sense to me why some of the people I was writing about who were doing things in the 70s, we hear about sometimes now today as well.
Gotcha. Yeah, it's curious. I don't know where it's going to go, but it's fun. It's fun to follow and it's fun to watch. Uh, and I have to say, and I guess this, I want to maybe this will be our last question for your, the history part of this. I
Sure.
think um, it's really difficult to tell where the magic of the science ends and where the magic of speculation and the magic of everything else begins. With a lot of topics, UFOlogy and quantum and consciousness and energy and what do you call it? What Uri Geller specialized in. A lot of this ESP type of stuff.
Right. Right.
It's very difficult to tell where the science starts and ends and where everything else it connects. You said earlier at the beginning that, there's parts where you kind of a little bit more sympathetic to and parts where you branch off. How do you discern? Like, how do you sort through everything, and what's the best way that you gather your
Mhm.
information?
A great question. So that's also one of the questions that really kind of helped me organize the book, to be honest. That is more of a
I
maybe
bet you needed to, right?
it's a classic question in the history and philosophy of science and sociology of science. It's often called the demarcation problem. How do we demarcate kind of
Mhm.
legitimate science from things that might turn out to be something else? Pseudoscience is a term that's often used, whatever you want to call it. And many philosophers have tried, frankly, very valiantly for at least 100 years in the modern era, and I'm sure we can find anticipations, to try to make criteria. If you meet this checklist, you're doing real science. If not, then beware. And what's really fascinated me as an historian, reading sociologists, even other philosophers, that kind of checkbook criterion list just has failed every time. I mean, just empirically, like, it doesn't that you should have a PhD from this such an accredited department. Well, okay, check. Whatever or you should publish in peer-reviewed journals. Well, there are lots of peer-reviewed journals on things that many of my colleagues wouldn't consider, legitimate science, and on down the list. So I think part of what I found so fascinating about this group was that they really are straddling. I mean, they're in that exact borderland. Often we learn a lot, right, from
It's a
borderland.
twilight zone, it feels like, for
Twilight,
sure.
yeah.
Yeah.
And so they're coming at it, as I've said 100 times, with really careful, deep disciplines training, which I could admire. And they're being open to a wider range of questions than was typical, partly, I think, because of their interests and personality, partly because of this very rapid change in how they were going to do their research and who would fund it and where they'd do it. So they were bringing to genuinely hard questions some really careful scientific training, framing things the way physicists are trained to frame them often,
Mhm. Mhm.
and trying to broach a broader set of questions than had been typical then, and frankly might even be typical today. And as I say, the fact that I might not consider each of their answers the last word, that's okay. That's
Sure.
how it's going to be. But what I got excited about was finding in the midst of this kind of unusual combination of topics and questions and methods, some things they really, really helped clarify for the whole community in the way that we put them in opening pages of our textbooks now, and they were just really a muddle or just not really understood as recently as 50 or 40 years ago. I find that
Mhm.
amazing.
Yeah.
We've had quantum mechanics now for 100 years, and the fact that we can still learn things about that, sometimes from people asking stubborn, awkward questions with the right tool set and really pushing on things that look paradoxical. I found that really exciting, and that's why I wanted to not just kind of brush aside these colorful characters, not just endorse everything they would claim, to say, what's it like to ask hard questions under unusual times? And there's a real legacy, intellectual legacy,
Mhm.
for us,
Mhm.
even narrowly in this field, that I think we should be very proud of.
Yeah. So, from your perception at the moment, what do you which of these kind of fields are you more sympathetic towards that you think could be a little bit more scientifically rigorous and I guess maybe even if we're lucky replicable? Because one
Yeah.
thing I again when mentioned Heather Spence, the marine biologist earlier, was we were talking about how with enough, like, obviously science is detecting patterns, but you always have outliers, and at a certain point, the study of the outliers become part of the science itself.
Yes.
So, what do you when you write about this? Which ideas are you more sympathetic to rigorously testing, and which do you think kind of deviate from what we're capable of right now?
Good. And maybe that's a great question. Maybe I'll start by saying one thing that I got a chuckle over when working on the book was things that were once seemed to be so intensely radical and strange, which you wouldn't raise an eyebrow now, not scientifically, but like
Yeah.
these folks I'm writing about and the San Francisco kind of counterculture movement more generally, these were some of the earliest adopters in the US of things like vegetarianism. Can you imagine
Right.
how radical? Of like yoga. I mean,
Yeah.
gonna
Yeah.
raise an eyebrow now, or very few people will. And so that things like that can move from really strange sounding out there to be like so mundane and ubiquitous over, 1 or 2 or 3 generations. What might be the comparable example within the sciences, I think is kind of a way of framing your question. Now, I don't know if I knew what the next hot thing would be, I would just work on that. So partly I would pretty
Well, you are. We'll get to
well,
that.
that's
Right.
my favorite. I do okay, so closest to home, what I really personally have benefited from, and maybe this is a nice pivot for other things we get to talk about, would be the really careful study of strange sounding quantum phenomena like quantum entanglement. That's now
Mhm.
as mainstream as it could be. It's the center of a multi-billion dollar industry, let alone a study of intense study by by people at universities. And that was really, really on the outs. It was really marginal merely 50 years ago at
Mhm.
the time that I was writing about.
Mhm.
And that's I've gotten to be able to learn a lot and build a whole group together and dive into that, partly inspired, honestly, from this historical study, and partly inspired by what the community had learned in the interim about these very niche or very esoteric topics. So I'd say what's often called the foundations of quantum theory, the what does it all mean stuff, like you mentioned, double slit, like Schrodinger's cat type question,
Mhm.
like entanglement, which is among the juiciest that is around. Those are here to stay, and now there's no one who would say those are kind of, not mainstream, but it took a while, and now they're the center of attention, and oftentimes even the center of my own attention. I'm
Yeah.
grateful for that. I got into that as a research topic partly because I was working on this historical book. So that was a nice bridge.
Yeah. Yeah.
Uh, Other areas, and here's where I don't know about them as nearly as well. I think the nature of human consciousness is just really hard. It's often called the hard problem or something like that. And I think it will continue to be.
Mhm.
Whether there are deep insights to be learned by taking quantum physics seriously and applying it to something like a very hot, wet human brain, where quantum effects are usually not most prominent, they get washed out. Some people are working, around the clock on that. I'm not. And that's something that was a deep inspiration for the folks I was writing about. Again, I'm not going to say every one of their ideas will come true, but that's a topic that is getting more and more attention in ways that it wasn't, even a generation or two ago in quantitative neuroscience, some kind of, border areas with not just chemistry, but also even with areas like quantum physics. And I don't know,
Yeah. Yeah.
but if people can be asking these questions and again in the careful, disciplined ways, the way I think they are, hopefully that's an area ripe for some real progress.
Yeah. I was talking to someone yesterday. I did a recording with the professor of philosophy at Rice University the other day, just yesterday. And one thing that we were talking about that he said that, people really struggle with, he goes, it's really difficult to tell whether something is a symptom of consciousness or the source of it,
Mm,
And so, we were talking about how, for example, if I walk into the room and he's in the middle of reading something very intense and he doesn't react when I walk into the room and I'm like, this guy can't be conscious, like there's nothing going on over here.
right.
And he's like, my interaction with you is a symptom of consciousness. I,
Mhm.
I I am conscious in my own head. And
Right.
I said, well, what's to make us think that our sense of self isn't also a symptom of some kind of consciousness that we're tapping into,
Mm,
and we don't, and he goes, basically, we don't have an answer, and it's just like, and
yeah.
it's really difficult, and that's what we're working towards. Um, I would love your explanation, perhaps, and thoughts, and maybe you can explain a little bit. The I want to basically spend some time on the relationship between consciousness and quantum physics,
Mm,
and why the double slit experiment was so important. Why and I mean, his name pops up in a bunch of different ways, but Jack Sarfati built another variation of this for what he called faster than light communication.
Right.
Um, and how does our sense of consciousness or observation impact the world around us for anyone that, on a basic level, I guess, and
Yeah.
how does the double slit experiment lead into that? So take that as you will, as you
Good.
will, and I would love to understand that.
I'll do my best. So let me preface by saying I'm not sure that quantum physics has much to tell us about consciousness,
Okay.
but I'm just saying I'm not sure. It doesn't mean it
Yeah.
doesn't, right?
Yeah.
Um, and that's one of these areas, as I say, that today is being studied very intensively by other folks. So they'll others will know much more
Well,
about.
why would we think that it would be,
Right,
or would it be?
exactly. So quantum mechanics on its own has some very, curious features. Even 100 years, they still make us at least scratch our head, and sometimes even more than that. Um, and one of them has to do with something it's often called the measurement problem. And the idea is that quantum mechanics, the equations seem to predict likelihoods, probabilities for outcomes with, as we now know from 100 years testing, incredible accuracy.
Mhm.
So, if we were to prepare a system the same way 10 million times, I always joke that's why we have graduate students keep doing these things boring. I'm teaching, like really careful, repetitive things. Then we can use the equations of quantum mechanics to predict the distribution of outcomes of those 10 million trials. It won't be the same outcome every time because of things like the uncertainty principle and all these kinds of things. But nonetheless, we can calculate really carefully with high accuracy the distribution of outcomes when the dust settles after those 10,000 or 10 million trials. Okay.
I'm sorry, real quickly. I'm sorry, just real quick. Can
Yeah.
can we today, instead of taking the time to have grad students do that, can we have AI run through a test 10 million times in a matter of minutes? And would you trust that? Would you trust that as a scientist?
Good. And so I think AIs are doing this now. What they're doing is simulations,
Right. Right.
essentially. And as I understand it, they're simulating probably based on the equations that we trust, which is maybe not testing those equations. That's like saying the equations would say this, can be very helpful. But
Mhm.
that's different from saying, are the equations right? Are they
Okay.
correct?
Gotcha. Okay.
So that's where I would maybe draw a little distinction there. I think, yeah.
Cool.
Anyway, so there's this puzzle because on any given one of those, 10 million trials, we get a definite outcome. We're going to ask, will the particle be found, over here or over there? That's essentially a kind of, we can ask yes, no questions. Is it going to be found here? Yes or no? Is it going to be found here? Yes or no? And quantum mechanics gives us a way of saying the likelihood that it'll be found here is 17.12583% or whatever it's going to be, right? Really hyper precise. And if you do this 10 million times, you find out, wow, it was found there exactly, with that
Wow.
proportion of time. So it's incredibly powerful. We have reason 100 years on to keep trusting this strange seeming theory. What the equations of quantum mechanics cannot do is tell us on this particular run, the ball will be found there instead of there, or the particle will. It'll tell us likelihoods. So then the question is, well, what converts this likelihood to a definite measured outcome on any given?
Mhm. Right.
That's a very different kind of thing than saying, just do this over and over again and see what the distribution of outcomes was like.
Because you're not certain until you're not
Until
certain.
It's not certain until a measurement's been completed,
Exactly.
and then
Right.
okay, this thing clicked, that thing didn't click. It was found there. Okay, so that we get definite answers. I mean, to be sure, I want to be clear. It's not
Mhm.
the world is only ever fuzzy. We can get arbitrarily precise answers. What we can't do typically is predict what that answer will be uniquely on a given trial, on a given one time. What we can do is say, do the same experiment as often as you can, and here's the likelihood you'll get that outcome versus outcome. And that's already incredibly powerful. That's what leads to things like computer chips. And we use this all the time. That's not like
Mhm.
only something cute to be able to do. That is really behind the entire consumer electronics revolution and what's to come. So
Wow.
let's pause and say that's already pretty great to even have that level of control of understanding of these physical systems. So one idea, going back to some very, very smart, in fact, Nobel laureate winning physicists, was that could the role of a human observer be playing a role in determining the outcome?
Right, because we don't know what the state's gonna be until someone's there to observe it.
Are we somehow what's often called collapsing the wave function? In our active observation, have we forced the system to choose, box A instead of box
Right.
B, even though ahead of time we just had a range of likelihoods? Now, I want to be clear, that is by no means the standard or most often accepted interpretation today. Historically,
What's the
but in
alternative?
what's that?
What's the alternative? I mean,
Well,
how is that how do you remove the observer from that?
there are a few alternatives. Let me just first and say that
Sure.
this was a favored explanation from some deeply smart, deeply appropriately venerated quantum physicists. It wasn't, it wasn't like it was only an idea from a bunch of amateurs. I just want to say that with the intervening 50, 60, 70 years, that's not the only answer on the table, and it's not even the favored one now.
Okay.
But at the time I was writing about, especially in the 1970s,
Mhm.
this was still among the more straightforward ideas that
Mhm.
something like humans would be, or maybe anything with consciousness. Maybe it could even be I don't know if an amoeba would have consciousness. So it didn't have to be a full human person. That there might be some role for consciousness in fixing the outcomes of otherwise probabilistic quantum
Yes.
scenarios.
Yes.
And that's what yields a definite measured outcome and not just a play of probabilities.
Right.
And I say Nobel laureates thought of that, not just as well as other very smart people in their own right in physics. And so that led many of the folks I was writing about to say, well, could it be the other way around? Could it be a two-way street? Right? If something like human consciousness might be playing some key role in determining quantum outcomes, could quantum processes in something like the human brain be playing roles in the outcomes of human consciousness? That's a
Mhm.
perfectly good question to ask, and many smart people are asking it still to this day. I don't think it's a bad question at all. I think the reason I tend to be skeptical, as indeed, be clear, I don't study this particular question head on. But what makes me raise an eyebrow about that human consciousness might be based on on unreducible quantum outcomes, right? Is that the very spooky, strange quantum phenomena that we otherwise pay attention to, like Schrodinger cat states, so-called superposition or entanglement, which we can talk about, that these tend to be actually fairly fragile. It takes a lot of work in the laboratory to preserve such a special quantum state and measure it precisely, because otherwise it tends to get washed out. It does what we often call decoheres.
You mean
So,
the connection between them gets washed out?
for
The
example,
bond?
yep, yep,
Okay, gotcha. Yeah, sorry.
or even for a single object being caught between two possible states, the Schrodinger's cat type
Uh-huh.
thing, that it tends to collapse, tends to go
Right,
into
right,
a
right.
definite state unless you're really careful.
Uh-huh.
And what are things that will make things collapse to take a definite state, or will wash out the special entanglement between two quantum particles? Tend to be things like sources of noise, ambient stuff in the environment. Um, and one thing that counts as noise is like thermal energy, like being in a hot room, like I'm
Yeah.
sweating now. Guess what's going on inside our brains, right? We're even hotter than our environments inside. Our body temperature is, like 98 point something degrees Fahrenheit,
Mhm.
even hotter than a typical hot day. And that's what's going on inside our heads. So there's a lot of thermal noise. It's also hot, wet, and dense in our brains.
Mhm.
Thank goodness, right? We need that for, chemicals sloshing around and so on. All these things, typically at least, are kind of enemies of pure quantum states. Quantum states will typically going to wash out, will lose their Schrodinger cat superposition, will lose their entanglement, will get literally washed out or decohered, typically on an incredibly short time scale in the presence of this kind of noisy thermal environment. So that's not proof that quantum mechanics has nothing to do with human consciousness. That's why I wonder about
Kinda
some of the
right.
stronger
I
claims.
understand.
You see what I
Can
mean?
I hope
Yeah.
I hope this isn't a silly question.
Yeah.
I did a podcast with a guy named Kevin, Hickerson out of Caltech,
Mhm.
nuclear physicist, sweet guy, great he's a stand-up comic, very funny, very sweet guy,
Yeah.
and one thing that he does is he studies cold neutrons, I believe. So he has to so he cl- so what he, the way he explained it to me was that by freezing them or by making the environment extremely cold,
Yeah.
the their actions slow down, making them much more easily observable. Uh, is this something that could be applied to to what you're describing? Because for example, you said our head is hot, 98 degrees, 99 degrees.
Yeah.
If you were to cool that down,
Mhm.
I mean, obviously, in our own in a physical body like ours, it probably cause enormous risk that you might not want to do otherwise. But
Right.
in general, studying this type of stuff, does cooling down the temperature of the environment make an impact on our ability to study it?
It all for many, many physical systems, it does. As a great example. So the neutron's a good example. There's a phenomenon, another quintessential quantum phenomenon with the name Bose-Einstein condensation. It's a name for physicists, Bose,
Mhm,
Einstein, and they both predicted. They kind of worked it out through some letters, and they figured this out that certain kinds of quantum particles could actually coalesce into one kind of act coherently, almost like the Borg. If people are like Star Trek Next Generation fans, it would be as if you have many seemingly independent moving parts that all act with real synchrony.
mhm.
But that's an example where to make that work, you typically have to cool these things down practically to absolute zero because that very special quantum state, gets easily disrupted in the presence of things like thermal noise. That's an example.
Mhm.
One of my colleagues at MIT shared the Nobel Prize for first demonstrating that back in the late 1990s with these classic experiments. And one of the hardest parts was cooling the stuff down in a controlled, reliable way because you have to get back then, I had to get super, super, super cold. So, oftentimes, indeed, by reducing the thermal energy, some of the more kind of basic quantum phenomena have a chance to survive and really
Right.
be measured more carefully. So it's not that the world stops being quantum. It's a messier picture when we raise the temperature back up to 98 degrees Fahrenheit, where these very special quantum coherent phenomena tend typically to get washed out.
I see.
Yeah.
I see. Very cool. Okay. So you have the observer, you have this, you have the potential issue with it that you just described. Um, what's another potential solution that we have today that or perspective that we have today that we didn't have at the time, or that, it's kind of emerging?
On the nature of consciousness, I'm not sure, but more generally about directions for quantum physics, I'm not
Hmm.
sure.
Hmm.
One that I've mentioned a few times is this really surprising notion called quantum entanglement, and that was really at the heart of the hippies book as well,
Yeah.
the heart of some of my own more recent research in physics. It's an incredible topic. I think it's even stranger than Schrodinger's cat, which is pretty strange, right?
Yeah, and it
That
also became a pop term. I think Ant-Man and Marvel helped turn this
absolutely,
entire
no, that's
world
right.
into like a
We
socially normal. It's part of the conversation now.
we've made the leap to the Marvel verse, right? The Marvel
Very
Cinematic
exciting.
Universe, which is a
Yeah, so
great
maybe
part.
you can explain a little bit of quantum entanglement then, or at
I'll,
least the premise.
I'd be glad to try. So the idea is that it involves two or more particles. Simplest thing about just a pair of particles. If they're prepared a certain way, and we talk about that, but if there's a way that now I think we understand really well, and then they're sent off, in opposite directions. They could travel arbitrarily far apart. And I don't just
Right.
mean between here and my office. It could be here and like Alpha Centauri or the next galaxy. In principle, really, really, really could be absolutely across the universe. And yet these particles will share a kind of coordination that has no analog in our classical system. If we did this with ping pong balls, they would not show the effect I'm about to describe, even if we treated them with great care. So the idea is if we prepare this pair of particles and send them on their merry way, and we perform measurements on one member of that pair, we have a choice of what measurement to perform. We want to measure certain properties of that particle. We can talk about what they are, as many long
Mhm.
list it could be. I like to think it's like we're going to ask a question of that particle.
Yeah.
Um, and then whatever answer we get here, and whatever choice we made of what question to ask, the outcome of a question asked on its partner arbitrarily far away will line up with it much, much, much more often than chance. And that isn't supposed to happen. That doesn't happen in our in
Right.
our kind of macroscopic world. And you can now test this really with high precision. It's not just lost in the noise. It's like remarkably more often than chance would ever allow. It's a much stronger coordination, a kind of connectedness that persists across space and time. And that is something that the equations of quantum mechanics predict. In fact, Albert Einstein and Erwin Schrödinger both helped identify that in the
Uh-huh.
1930s. And they both thought this is so wacky, that can't be right. So they both thought that's one more reason to be skeptical of quantum mechanics. They both helped invent quantum mechanics. And this was, in some sense, for each of them, one of their breaking points. They
Mhm.
said if the equations say that should happen, Einstein famously called the spooky action at a distance. He said, that's ghost
Mhm.
book. It's not science.
Mhm.
They said if that's real, then quantum mechanics is at fault, not the world. And generations later, including some efforts from some of the folks I wrote about in this book, and now really fancy modern experiments that my own group was able to do, and many, many around the world now, we can test this, up, down, and sideways with very, I think, clever, careful experiments, shielding against all kinds of, kind of alternate explanations. And we find really, I'd say by now, beyond the shadow of a doubt, that this quantum effect is real. The world works that way, and it's hard to show it, which goes back to like it's easily washed out.
Hmm.
But with very carefully controlled laboratory experiments now, we can do this across huge distances in many, many tens of thousands. Well, let's see, kilometers, certainly tens of thousands of meters at least,
Hmm.
and the signal stays holds up. So that's something
Crazy.
where it's nutty.
It's so
And
crazy. I mean, because what you're essentially saying is that and I actually meant to ask, do these is this contingent on them having to interact to begin with?
it is.
Um,
That's
so
right.
me and you meet in person,
Yep.
and we separate. You go to Australia, and I go to back to the States, right?
Yep.
And that distance between us does not seem to have an impact on the entanglement that we might experience together.
That's exactly right. And so what's strange about that is, by the way, if someone who's sitting, asking you questions in the United States, doesn't know that your answers are lining up with the answers I'm giving in Australia.
Right.
So that's something that's actually really important. That's subtle. That's part
Because
of,
that removes the observer that we mentioned earlier.
well, it's because your answers will look to be a series of random yes nos.
Uh-huh.
We frame those kind of yes no questions. Let's say +1, -1, coin flips, any
Yeah.
kind of question for which there's only two possible answers. It makes it cleanest to show.
Mhm.
But that's
Mhm.
the cleanest version. So if it looks like you're flipping a fair coin. You say +1, +1, -1, -1, +1 in a thoroughly random pattern. And then it turns out I'm also giving, if you only have my logbook, what are the answers I gave? Totally random set. And then when you bring the two logbooks together,
No.
that is spooky. That is weird and spooky. And so sometimes people say, oh, it's not so strange. It's like a pair of gloves. If we both, meet in Harvard Square and I hand you one glove and I take the other one, then whatever it was, you have a left-handed glove and I have a right-handed glove and they're going to line up. They're going to be coordinated. It's not that. And let me be clear. That Einstein would have been perfectly happy with that kind of coordination. Entanglement is much, much spookier, and it really can't be kind of faked or mimicked with objects that have definite properties at all times. That glove that might have been sealed in a box was already left-handed before you opened the box. If it's an actual macroscopic glove you could put in your hand. If the little particle spinning and you say, what's it spin along the x direction, even assuming that it has a definite answer for spin before measuring it gives the wrong statistics.
Mhm.
Somehow these objects, the properties they have themselves are being coordinated at a distance in real time to keep
Yeah.
these answers lining up, even though we could do this by asking different questions and it didn't actually always have to have spin up along it. So it's not that it had a definite property that was revealed.
Mhm.
So the properties themselves seem not to be fixed ahead of time.
Right.
And that's part of what goes into our notion of Schrodinger's cat and superposition. And now we're supersizing that strangeness across a pair of objects across the Earth or the universe, asking a pair of asking different questions as measuring different properties, not just say handedness of the glove.
Yeah. I
And
think
so
what was it? Is it the twin experiment that you quoted in your book with the beer and the wine and
exactly right. That's right. So I tend to think about it. Actually, I have twins. My kids, I've
oh, that's cool.
boy
My
girl
wife's
twins.
an identical twin.
And so we worked this out. Actually, when my daughter was homesick from school when she was like 7 or 8, we were talking about this.
Okay.
He gave me the following. So I wasn't talking about getting sloshed in the bar with my 8-year-old daughter, but we were talking about dessert options, which seemed
Okay.
pretty good. Got her excited about science. So one question could be, what's your preference for baked goods? And you
Mhm.
only have two answers. A brownie or chocolate chip cookie. Those are pretty good answers. But in one question, baked goods.
Yeah.
Right? And sometimes you go back to the same restaurant and they ask your preference for frozen goods, ice cream sundae or frozen yogurt. Great options, right? And then likewise for your twin brother who's in Australia or on Alpha Centauri, wherever. So whatever the question is, there's a +1 answer and a -1 answer. right? So we could say that the first thing you're at, the first option is +1.
Hmm.
What do you want for baked goods? Brownie. Okay, that's +1. Chocolate chip cookie, that's -1. So now you can code the answers, whatever
That's
the
right.
question was, right? And likewise for the frozen goods. Ice cream sundae +1, froyo -1. Great. Okay. Now, even as we shuffle the questions being asked, baked goods or frozen goods at random at each side, they don't have to be asked the same question at the same time.
Hmm.
We're going to compare how often they said +1, how often, no matter what question they were asked, the answer lined up. So you could have been asked about baked goods, I could have been asked about frozen goods, and we've still both answered +1 or -1 in sync in a way that looks like a completely random series of answers ahead of time. And it's not that we memorized our answers in advance, because there's a way to check for that too. So it's not that we said, +1, +1, -1, repeat the code. That won't work
Hmm.
either, it turns out. We
Yeah.
can shield against that too. So that's much more spooky than like it was a left-handed glove and I just opened the box. It's like saying, we could ask about the glove's handedness or its color, but not both. And we're getting those answers line up. So you open and get a blue glove, I open and get right-handed, and somehow that lines up better than chance. That's, or indeed these dessert orders. The analogies get strained. It's hard, but the idea still kind of makes the hairs on my head stand up, or I don't have
It's
any left.
crazy.
Um,
Yeah. On
right?
mine.
Y-
And mine
y-
too.
Yours and so that's something that the group I wrote about was really, really intensely, passionately curious about at a time when not a lot of physicists were, which is kind of nutty given how as foundational it is to how we describe the world. And then one member of that group I wrote about went on to share the Nobel Prize in 2022. Um, John Clauser, he was doing absolutely pioneering experiments to say, is that real in the world, or is it
Yeah.
only a prediction of these equations that might be wrong? First ever with a then graduate student, Stuart Friedman, he was working with. The two of them did these foundational experiments, recognized literally 50 years later with the credit that I say they deserved, from day one.
Mhm.
And then generations getting better and better at testing things. My own group did some pretty wacky, cool, fun tests as recently as 2017 and 2018 to really
About that.
nail it down.
What
And
what
now,
was what was your group's, test? What was that process?
so we call these the cosmic Bell tests. These are named for John Bell, a remarkably gifted physicist who passed away far too young. But John Bell came up with this way of testing for entanglement versus something more like an Einstein-like universe, where things would have definite properties and you just reveal chance correlations. And John Bell said we could design experiments, real laboratory experiments that could do that. He was a
Mhm.
theoretical physicist, but he laid out how to design a kind of protocol. So we
Mhm.
call these Bell tests in general. And then my own group did cosmic Bell tests. Part of what I mentioned briefly a moment ago was that you want to have some source of randomness in deciding which question to ask. In the analogy, it's like, does the waiter ask about baked goods or frozen goods? The waiter can't tell you the answer. That's what the particle says. I want a brownie. I want an ice cream sundae. But the waiter, our experimenters, decide what question to ask, what type of measurement to perform.
Right.
We want those to be as uncorrelated with each other as possible. We want random choices at each side of what the questions to be asked in what order.
Mhm.
Okay. So people have come up with all kinds of random number generators, and we said, yeah, but we could do better. We have this whole big universe out there. Let's turn the universe into a pair of random number generators. Let's make the universe work for us for a change, right?
Yeah.
And so the way we did that was we get these beautiful, beautiful large telescopes. We had to do the final experiment on top of one of the Canary Islands called La Palma. It's this tropical paradise off the coast of Morocco. And
Amazing.
on top, they have these enormous world-class telescopes. Some of them had mirrors 4 meters across, like 13-foot mirror.
Wow.
You can see really distant, faint objects in the sky with these things, much better than the typical telescope. So we did this experiment. We shipped down a laser from my colleague's laboratory in Vienna. That's where we made these entangled particles in a cool way I can talk about with a pump laser, shoot them across the island at night. It's very romantic. And then the particles go out towards two huge telescopes in a straight line on the island, these enormous optical telescopes. After the particles are emitted, so after the entangled pair has been created, with whatever properties they might or might not have, they've left the station, right? They've stopped interacting. They're traveling at the speed of light in opposite directions across the island. After that's happened, and before they reach their detector, we use these enormous, gorgeous telescopes to take in basically random numbers from the sky, from parts of the sky that basically had no chance to coordinate with each other. That's why we want to use the huge expanse of space. What Carl
So what
Sagan
you're
would
essentially doing is you're making a enormous playing field, and then you're just throwing two coins, and like you're like, you know what? I could throw this into the pond, or I could throw this into the ocean, and I could take an airplane and I could drop it, and you're doing that with the galaxy.
we are. So that's right. So we're taking as distant a source of random inputs as we could from opposite sides of the universe that hadn't been
Incredible.
talking with each other, practically since the Big Bang.
Wow.
So like so the questions we asked really shouldn't be lined up. The order of questions should be unknown to the particles because the questions weren't even determined until they left the station, right?
Right.
While they're in flight, they're no longer together, they're moving at the speed of light, but before they reach their destination, we're taking in random numbers from opposite sides of the sky based on the color in the tiny fraction of a second, roughly a millionth of a second, the color of light from some distant, very, very distant early galaxy, a quasar, two different ones that they themselves didn't have a chance to talk with our station or with each other, since forever, essentially, since the dawn of time.
Right.
Um, so we're using, again, what Carl Sagan would call the billions and billions of light years of space and of years since that light was emitted. And we're making a snap-second measurement of the colors. It's slightly more blue or more red than average. That tells us what measurement to perform on the earthbound particle that's coming toward that detector. That's like saying if the light from the very distant light on the sky in that millionth of a second was more blue than typical, more blue than average, then ask the particle about baked goods. Right? That tells you what question to ask. If the light from the distant object in the sky was more red than typical, then ask the other question. Ask about frozen goods when the earthbound particle arrives. Do the same thing to its now separated pair on the other end of the island with inputs from a totally different, nearly causally separated source of randomness. That was crazy fun. It was amazing. And we were able to do this for, tens of thousands of pairs of particles. So get really good statistics and show it's exactly what quantum mechanics says it should be. And we can't explain it by any kind of Einstein-like conspiracy. It can't be that the particles actually had properties, but they knew what questions they'd be posed. It can't be that they kind of had the pop quiz ahead of time and knew to study for the right answers. We're finding to exceptional statistical, accuracy, the predictions of quantum mechanics, these answers lining up, even when they're being asked random questions that were unknowable in advance, and
Hmm.
they're being posed these questions significant distance apart. So that's not the end. People do even cooler experiments now, but that's the kind of generational legacy you see. The phrase extraordinary claims require extraordinary evidence.
This is
It
pretty
really,
extraordinary evidence.
I felt like it was. This in combination with many cool experiments from many groups around the world, we say now like the jury's back, like the evidence is in. And that really is a journey
Hmm.
that began in 1935 with incredibly important articles by Albert Einstein and his younger colleagues, by Erwin Schrödinger, by incredibly important work in the mid-1960s by John Bell, by these really careful thought experiments and real experiments by the hippie group that I was writing about, including John Clauser and other of his colleagues in the Berkeley area group were thinking hard about this, on and on, up to the folks who shared the Nobel Prize just a few years ago. It's nearly 100 years of grappling with this, and it's not only because that's how the world seems to work, and wouldn't you like to know, but now because this phenomenon is at the center of this multi-billion-dollar industry,
Yeah.
which our next generation devices will only work as designed if that's a feature of our world, if we're not fooling ourselves by some curious thing we'd overlooked in our previous experiments. So now it has actual practical implications as well as some of the most, kind of out there sounding basic science that I can dream up. So for me, it remains, as I say, just like delicious. And one of those things that I got to really dig into with my physics cap, only having sat with that historical work to say, what did people wrestle about? Why did they care? What could we do better today than what they had with their own tools? The two projects fit together really nicely.
It's amazing. It's so freaking cool. I mean, I while you're describing these experiments,
Mhm.
or while you're describing these ideas, I was curious. The question jumped to my mind: is there a connection or dare I say, one-to-one relationship between the rules of the quantum world and the rules in the world that the physical world that we're in ourselves? Or should it be, and we haven't gone there yet? How does this work?
It's an amazing question. So the short answer is we certainly believe there ought to be,
Right.
and
I think so too.
and yeah, and we don't know. So sometimes it's called the so-called quantum to classical transition, which is like,
Mhm.
how come when I'm describing ping pong balls or soccer balls, right, during the World Cup or whatever you want, or cars on the road, we don't have to use any of these strange sounding ideas, right? The car is not in a superposition between the left lane and right lane the way Schrodinger's cat is alive and dead. We don't, right? My car is not spookily entangled with, some car in Australia. We can test to make sure it's not. We know it's not.
Right.
And so what's the scale? What's
Yeah.
the size at which you have to use those rules, those funky, strange sounding rules from quantum mechanics? And what's the size at which we get to use the rules of let's say, ordinary experience or formalized things like Newton's laws or Maxwell's laws or even Einstein's laws of relativity, which can be more exotic than me driving down the road, but still don't have that quantum feature.
But I'm sorry to interrupt.
No.
The For example, let's say communication, right?
Hmm.
Like you and I have spoken before, and our cars might not be quantumly entangled, but thoughts we don't really know how to measure as something that's classical, right? Like we would say, would that be something that would hypothetically be privy to this relationship? That thoughts would interaction would things that like laughter, like these emotions that we can't really detect on that way might be more detectable on a quantum level.
It's possible. Again, it goes back to why personally I'm skeptical. I don't want to say it can't be, but it
Yeah.
comes back to to my thinking, that would seem to require hot, wet, dense human brains, right? Not to wash out these very special, very fragile quantum
Ah,
correlations.
right,
It goes back
right,
to at least as I think about it, and I could be
right.
I'm right, but that actually comes back to my own thinking, at least about how hard we had to work on that island, not to let those quantum entangled particles get washed out before we did our measurements.
Mm.
And
Mhm.
and that's really different than, I think it's really different than a kind of quantum
So it
entangled.
could just be the setting, you think? It could be hypothetically the setting, or I mean,
Well, if we're getting around to kind of conscious people, then they're gonna have high temperatures and wet, dense brains, and those tend to be the enemies of really subtle quantum effects. That's what I
yeah,
would.
yeah, yeah. What about things that alter our state of awareness or being, like breath work or psychedelics or something like that? Which I'm sure, again, this is all the same Eastern stuff, San Francisco stuff that came
Yep,
directly from the East. That's like the first place they stopped over,
right.
and we know that. Listen, we don't know what those are is I guess the real problem, right? Like I can't measure when I'm doing breath work and I have a out of body experience, or I interact with the soul of my grandfather, something like that. We can't really put that on a scale and say, hey, what are we doing over here?
I totally agree, and I'm not gonna say those phenomena aren't real. I'm saying I don't know how to make sense of them. I wouldn't appeal to those first and foremost in terms of quantum mechanics these days.
Gotcha. Yeah, yeah, yeah.
And
I got you.
and that's partly because 'cause we've learned a lot, partly because of all the hard work that this hippies group did. Some of them would still advocate that, and they might be right. I don't know.
Uh-huh. Sure, sure.
But it's a fair question, and it was I think, frankly, a more fair question 50 plus years ago before the community had learned more things about things like quantum
Mm-hmm.
entanglement and
Mm-hmm.
how to really manipulate these states. So I think some of these questions, as I say, have been productive, even if they turned out to have been wrong,
Right,
they led into a line of inquiry from which we've learned. So
right.
again, I don't dismiss the effort to ask those questions. Today, if I were to be a betting person, I wouldn't personally bet on that, but that's me, and that's from where I'm sitting. And
Sure.
and for me, it comes down maybe stubbornly to this notion of, even with my careful breathing exercises and other things, it's not like I've been thrown into a cryogenic chamber and the individual quantum particles in my head are now moving around, a few degrees above absolute zero. They better not be, or else I wouldn't come out of the experience. So that's where stubbornly myself, maybe it's my blind spot. That's where I have trouble seeing that today. And
Uh-huh.
I can say that with confidence, partly because now I'm the beneficiary of 50, 70, 90 years of people thinking hard about things like quantum
Yeah,
entanglement. And that's
yeah,
good. That I want to celebrate, right? That's pretty great.
yeah.
Yeah.
I want to take the last bit, and if you have a couple extra minutes to go a
Sure.
little over time, I'd appreciate that. But it's totally,
Absolutely.
whatever you want. Your recent work on black holes, tiny black holes,
Yep.
primordial black holes,
Yep.
and then I ran into, and I think you wrote about this in your book, which is why maybe I did a little bit more homework on it. I don't remember whether you wrote about this or not, but the debate between Stephen Hawking and what was the other gentleman?
Well,
About,
we had a bunch of debates, but I'm not sure which one you have
oh,
in.
sorry, about whether or not information could leave black holes, and whether or not, and I'm curious about how you got to this new stage of research from
Sure.
there. But does the size of a black hole, do you think, does the actual physical size of it carry the potential for more or less information that could come out of it, or we don't, or we still have no idea?
It's a great. So the last question is a great, great and hard question for which I don't have a clear answer. So my colleagues will tell
Good.
you
Okay.
answers might not agree with each other.
Okay.
It's a
Gotcha. So we'll go back to the first question, which is how you got into this, and what piqued your interest in particular about this, and
sure.
how did
Yeah.
you pivot from this world to that world?
Well, so a lot of my work in physics from even from my undergraduate and graduate school days has been on the very early universe, like the time of what we call the Big Bang.
Mhm.
Not originally on the quantum physics stuff, though I've had an amazing time working hard on that too in more recent years. So my work has been on how do we understand what we call the Big Bang, and with the best ideas that we have about how matter behaves under extreme conditions, very high temperatures, very high densities. Um, can we build a kind of consistent model that would account for matter at impossibly early times and that could connect with things today and make predictions along the way? If this happened, we should see this on the sky. We should see that on the sky. This phenomenon might be real. Okay.
Mhm.
That's been incredibly exciting. It's still incredibly exciting for me. I've been
Yeah.
working on that essay since undergraduate years, which for me is like not so recent. So I love that topic. And as an example within that topic, I've been studying things like tiny quantum fluctuations in matter that would have been filling the universe when it was very, very tiny, very early after the Big Bang.
Mm.
Taking ideas from quantum physics seriously, like the uncertainty principle, we can't turn off some sort of unavoidable quantum jitters about matter at its most fundamental. And that has really interesting implications for how we think about matter at the earliest times and how those quantum jitters might get stretched as the universe itself expands over time.
Would they get thinner or stronger as they stretch?
Oh, good, good. So the wavelength gets much longer. So imagine that sounds like a rubber band,
Uh-huh.
and remarkably, the height of the wiggles actually tends to get more or less constant. You would think one might think
Interesting.
fall. That's really subtle. That's an interplay between gravity and quantum theory, which really happens on very large length scales. There's a kind of reservoir of energy coming from the gravitational field, which stops those fluctuations from falling in their height, in their amplitude, arbitrarily small. And we should be very glad about that, because that, in some sense, explains partly of why we're even here today. Now, that was a leap, but the idea is these quantum fluctuations in our matter fields in the earliest moments got stretched as the universe expanded very rapidly at early times. And that meant that there was a little bit of unevenness in the distribution of matter and energy in the early universe, a little bit lumpiness at a small level, but not a zero level.
Mhm.
The level freezes out at something like 1 part in 100,000, a fraction of 1% different, where in the earliest times, there was a little more stuff per volume here than here. And
Mhm.
that's we as in our current best thinking, are a direct result of quantum physics now being thought about on the huge scale of the entire stretching galaxy. Now, if there's a little bit more stuff here than there, then gravity takes hold, and that little extra mass attracts more mass through gravity over time. So what started out as just slightly more massive than average
Snowballs.
snowballs, exactly. And now we get to a universe that today has this incredible patchwork structure. We call it large scale structure, enormous teeming hotbeds of activity, superclusters of galaxies, all kinds of hot gas swirling around, stars, galaxies, planets, and then enormous voids with nothing happening. I like to say it's like Manhattan versus where I grew up. That Manhattan stuff is constant activity. I grew up in the New Jersey suburbs, like nothing. That is a void if there ever was one.
Which part?
I'm
Which part
from
of Jersey?
from West Orange, northern part.
No way.
Yeah,
Love West Orange.
yeah, yeah.
It's so funny. You're validating my opinion. I haven't met someone from West Orange I have not liked yet. So
Well,
that's
there you
excellent.
go. There you go. The hometown of Thomas Edison, among many other notables before and since. Anyway, the point in making a joke at New Jersey's expense, like there are hotbeds of activity and then voids where nothing important happens. And I was teasing about my hometown. So that happens in the universe, right? So
Right.
and we really can trace that astonishingly well from these early universe quantum fluctuations. A little bit more stuff here than average. Whoa, let it grow over 14 billion years since the Big Bang, and now we have this really articulated structure. That's amazing. That's cool. Okay. One thing that could happen within that story is there could be even larger peaks of some of these quantum fluctuations on much shorter length scales than typical. It doesn't have to happen, but there are more and more ways we've come to understand where that could plausibly have happened in the early universe based on how we think these matter fields should have been behaving anyway. There could be conditions that make a large spike of these, like much more stuff per volume in a narrow region of space compared to the average.
Okay.
Those can then collapse under their own gravity directly into black holes. We don't know
Okay.
that they do, but it looks more and more compelling that they really could.
So I'm sorry, just to clarify, just to make sure I'm understanding correctly. So you have, p- I would there are you looking hypothetically for things that could cause these rapid shifts in mass, or these rapid gains, I guess, in mass? And then have you observed a point of collection of mass
Right.
before it starts to fall in? The thing that comes to mind is one of my favorite Calvin Hobbes strips where he's talking to his dad, they're crossing a bridge, and it's like the weight limit is 10 tons, right? He goes,
Right.
"Dad, how do you know how many?" He goes, "They keep on driving bigger and bigger trucks over until it collapses, and they weigh the last truck and they build a bridge again."
Right.
Like,
Right.
how do we know? How do you observe this as a scientist?
I love it. So what we haven't yet been able to do is observe this as scientists directly in the universe.
Okay.
These are hypothetical. But what we can do increasingly is run both, very careful pencil and paper calculations, but now where I find it even more compelling are very fancy computer simulations, which we can test against other scenarios that really do match what we see.
Ooh,
So we can do
cool. Right.
calibration. Doesn't prove the simulations are correct,
Right.
but we have reason for confidence in them.
Yes. Yes.
And these computer simulations can now evolve Einstein's equations from relativity better than like ever before, with fewer and fewer approximations because computers get better and people get better using computers. And like I say, we can calibrate those in other scenarios where we can have more direct things in nature to compare with, and those are
Hmm.
beautiful match. So it's not proof, but it's more
This
and
is
more
so
likely.
cool. I'm
Yeah.
thinking about just in real time, like, what if one collapse causes that wave to continue and then cause, and wow.
Right. And so we have a better understanding of what could have led to these early universe spikes in the
Mhm.
distribution. There could have been a lot of stuff here and then mostly just, nearly smooth, porridge, little lump
Okay.
porridge. Some rare, very rare but strong peaks. Now with pencil and paper now increasing with very, I think, impressive computer simulations, we can show if there really was that much stuff compressed into that small a region of space, which should happen sometimes, rarely, but maybe not never, then those really can collapse, according to Einstein's relativity, into the densest object available, a black
Mhm.
hole. We can't, if Einstein's relativity is correct, then no amount of matter can be squashed more densely than a black hole. And this stuff can fall all the way down into a black hole. And that can be happening sporadically from these extremely early universe quantum fluctuations, not just in the way we know that normal kind of boring black holes form. First of all, I love that now black holes can be born.
Boring.
These are astonishing things. But we now know for 50 years plus of very hard evidence from astronomers as well as from theoretical work, our universe is chock full of black holes. Not necessarily the ones that I just described that formed from the Big Bang. Those are hypothetical. I think they're well motivated. We don't know. The typical route by which black holes form that we really know about is from a star that lit up, is fueled by nuclear reactions in its core. It will at some point exhaust its nuclear fuel and then
Mhm.
gravity will win. Womp. If the star were massive enough to start with, the end state will be a black hole. We call these stellar collapse, star collapse black holes, and they're everywhere in our
Mhm.
universe. And we can measure them with gravitational waves. We can now even take a certain kind of composite photograph of the monster large ones in the center of our own galaxy. We have enormous evidence that stellar collapse black holes are real and kind of mundane. It's
Mhm.
So what I'm curious about is the second route by which black holes might have formed. The early universe quantum fluctuation thing goes directly collapse in a black hole, does not pass go, right? Does not form a star. And these could have formed before there were stars, before there were atoms with nuclei that
Wow.
fuel the stars, before there were protons or neutrons, when there was even a primordial soup of the parts that go into protons. Really, really different conditions by which black holes could well have formed, though we have no proof as yet for the second route, for these so-called early universe or primordial black holes.
Meaning so for the case with hypothetically the star, the one that we more commonly know that's a bit more pop culture-y that people are more aware of, like
Yeah.
Interstellar, right?
Yeah.
We know comes from a star, goes out, kind of collapses into itself, turns into a black hole.
Yep.
Before there was stars, what would be the mass that
Good.
collapsed?
So
What would it be?
it would be a hot, dense soup of the stuff that later would make people like you and me and planets, but before it condensed into the particles that we would recognize today. So it would be an early universe hot, literally a hot soup. We call it
Mhm.
plasma. It's a hot soup of charged particles. It would
Mhm.
include things like electrons, people might remember or have heard about. Those are in our atoms, today. It would include not necessarily protons or neutrons, but the stuff that goes into protons and neutrons, quarks,
Mhm.
mostly quarks, and the little particles that make quarks interact with each other called gluons. Gluons are the glue
I love
that
that name.
later on would glue quarks together into protons. That's a not very creative name, but that's what we call them. So these black holes that I now find so fascinating, these primordial black holes that really might have formed, that we don't know for sure, but they really plausibly could have formed, would have formed from these quantum fluctuations that made certain amounts of this goo, this primordial soup, basically quarks and mostly gluons, elementary particles, collapse under their own shared, gravity into black holes. And that means those black holes could have masses way different than the mass of a star or the mass of the black holes that otherwise
Right,
do a lot
right,
today.
right.
It's separate because it didn't form from a star. It doesn't have to have anything to do with the size of a star. And that's pretty cool. So black holes that we know about, stellar collapse or astrophysical black holes, can only be as small as massive as roughly the mass of our sun. A little bit bigger than the mass of our sun. They could be larger than that. They can't be smaller than that.
Mhm.
These primordial black holes have nothing to do with stars.
Right.
They form directly from these quantum fluctuations, which have their
Wow.
own rules about their kind of length scales. And so you could have black holes formed by swallowing these, primordial elementary particles like gluons and quarks, for example, and they could have the mass of an asteroid, but because it's the densest state of matter, imagine a huge space rock, like a real mass, not quite as massive as our moon, but close to that mass,
Mhm.
but the size of a single atom in space.
Wow.
So you take the mass of an asteroid and you squeeze it down to make the densest state possible, an actual black hole. It will be the size of basically an atom.
Can okay. I have 2 follow-up questions, but a
Yeah.
pop culture question that just hit my mind
Good.
because one fun thing that I like to do is I try to find science advisors for Hollywood movies because
Yep.
they're fun to talk about. They cross speculation with science. When Ant-Man, right, collects an enormous amount of force
Yep.
while he's shrinking while fighting someone, right? So he punches someone, and while he's punching, he's shrinking into the size of that little tiny Ant-Man thing.
Right.
That is all the force of the full, what's his name? Paul Rudd
Yes.
into the size of a fly. But so you have all that mass. It's just
Mhm.
the way that it's condensed or physically, I guess, manifested is much smaller, but it would hypothetically, scientifically be what you're describing right now.
It really could be. And so these things would pack a punch. And so my group and I, my amazing students and colleagues, have been wondering if if these things ever formed, there could have been a lot of them around the universe today. They
Mhm.
could be maybe all or part of what we call the dark matter. We can
I
talk
was gonna that's my that was gonna be my next question.
and,
Beautiful.
and
Let's
I'll,
so lead into that, please. Yeah,
well,
please.
but say if they are, then there should be a bunch. There should be a bunch even around our solar system.
Uh-huh.
Not a bunch on Earth. They're still too diffuse. There's not that many that we'd ever expect even a single one to hit, you or me or even the planet. But there could be like 10 between here and the planet Jupiter. Now, if you have 10 objects the size of a single atom sprinkled throughout space as big as the orbit of Jupiter, they're going to hit essentially nothing. But much like with your analogy, they have a large amount of mass
Mhm.
moving around at a high speed of 200
Mhm.
kilometers a second, 250 kilometers a second, much faster than the Earth moves around the sun, for example, they could be having effects in our even close to us in our own solar system without even hitting anything. So whereas Paul Rudd has to punch someone, right? These black holes could make the planet Mars wobble to a degree that we could measure from here just
Wow.
by zipping past it, not even hitting it, because it will interact with
Wow.
gravity.
Yeah.
Something heavy that moves fast will, exert quite a shove on some other massive object like the planet
Mhm.
Mars. And one of the first projects in this vein that my group and I did was really go through very carefully and build our simulations and try to really be quantitative, saying a black hole that could have formed from just after the Big Bang could be dispersed throughout the universe, could be playing the role of dark matter today. You could have a few of these sprinkled throughout our cosmic neighborhood.
Mhm.
And just by going on a joyride through the solar system and hitting nothing, could modify Mars's orbit enough that we would be able to measure that with the technology we have today. It would be like tens of centimeters. It would not Mars will not fall out of the sky. This will not become like a Hollywood disaster movie. It will be a little perturbation
Sure.
through
But
the
you could
motion
detect it.
of well-tracked visible objects whose locations we otherwise know really well.
Yeah.
Uh, that's pretty amazing. So that's the kind of thing we've been
And how
playing.
and how does this and then I'll let you go. I'm a couple minutes. I'm sorry. I'm having so much fun with this though. Is what so how does this answer the problem of dark matter? What's the complication behind dark matter? I spoke with the dark matter physicist on the show once before, and basically his attitude. I think when we spoke on the phone at first, I talked about this a bit, but that he's like, we don't know what it is. My career is basically throwing things at a wall and saying what it isn't until you find out what it is.
Yes.
And how does so what's the complication with dark matter, and why does what you're doing now potentially offer that a solution or an answer to that?
Good. Okay. So dark matter again is a long-standing challenge intellectually, conceptually.
Mhm.
It really came together as a sharp question 50 years ago, with hints even again going back to the age of the 1930s. We've been sitting with this in one way or another for a long time as a community. The idea is that when we look out on the sky and measure the motions of things that light up, that could be an individual star, it could be a galaxy composed of lots of stars, it could be clusters, across an enormous range of scales, we watch stuff move, right? And we can now, with fancy telescopes, watch stuff move with great precision. And what's been clear, increasingly clear in recent decades, and even hints of it going back further, is that across that huge range of scales, individual galaxies, stars within one galaxy, all the way out to huge massings of stuff, things move as if they're being attracted by more gravity than we could account for
Mhm.
just by adding up all the gravity from the things we see. So that's what we call this dark matter. We can track the motion of things that light up, stars, galaxies, even planets that reflect light near us. Right? We can track stuff through light,
Mhm.
either its own light or reflected light,
But that
and
only
we can
makes up
then
a tiny percentage of the mass that we know of.
exactly right. And so to make sense of the motions from individual stars in whipping around rotating galaxies to clusters of huge range, none of that. It's a huge accounting error, like the worst accounting error among the worst, because all these things, the motions make perfect sense if we say, oh, there's a lot of mass in that system that's not lighting up, it's not reflecting any light,
Mhm.
acting through gravity, and therefore affecting the motion of the lit up things we can track so carefully. And it's not just on the scale of galaxies, and not just here, it's across an enormous range. In fact, we can even infer that it was there in the earliest moments after the Big Bang from other things that lit up that we can, measure
Mhm.
carefully. So across literally all of cosmic history, across a huge range of length scales, we're stuck with it. What is this stuff that's acting through tugging on the stuff that lights up and changing its motion accordingly, and yet not lighting up on its own? Okay, it could be, as it sounds like your previous guest had probably had in mind, it could be some new particle. It could be a whole bunch of new particles
Sure.
beyond the ones that we know about. And that's the sort of throw things. People have been trying with great ingenuity and great skill, and so far zero results, zero results for 40 to 50 years. Say, oh, it's this new particle. We'll find it in this new experiment. It's going to interact this way. We'll know. And it's not, again, not to make fun of them. These are hard experiments that are done very well, with to date zero compelling evidence that there's even one new particle that fits the bill yet. And they could be there, and the experiments continue. Okay.
Mhm.
Another idea that comes up, which is perfectly self-consistent, it's a good idea to pursue, maybe our laws of gravity are wrong. Who says Einstein's the last word on relativity, or let alone Newton? That's a logically consistent alternative. And the challenge is, so far to date, the best efforts to do that kind of don't solve the problem. Or they'll work at one scale but break at other scales. Typically, people can make pretty cool models.
Mm,
They'll modify gravity just a little bit. We've tested gravity very well. So it's not like throw out the notebook and start from scratch. They're kind of tweaks typically. And the tweaks will often work to account for the effects of dark matter at one length scale, but then they break even worse than just plain old gravity elsewhere, typically. So
hmm
that doesn't mean that we're done with that route, but so far that route hasn't worked either. So it's not yet clearly new particles. It's not yet clearly new laws of gravity. What if, drum roll, what if it's these tiny, crazy little black holes that formed right after the Big Bang, have been scattered throughout the cosmos? They have
hmm
enormous mass packed into small
Yes.
space. Large mass means they're going to act through gravity. They'll tug on stuff.
Yeah.
And they're black holes. They're not lighting up and shining on their own. They're absorbing the light that falls on them. They are dark, right? Talk
hmm
about dark matter. It's like central casting. So that's gotten a lot of people excited. My own group, but lots of people around the world, many groups very active and very creative on this too. Doesn't mean it's right, but it sure is a pretty compelling possibility, especially given all the hard work that continues,
hmm
but so far has not quite nailed the challenge of dark matter in either its new particles or its different laws of gravity. So we want to say, what if it could be ordinary matter we already know and love, like these elementary particles I mentioned, quarks and gluons, say. We know those are part of our world. We know that black holes exist in Einstein's relativity. So what if we take known particles and known features of gravity? That's pretty conservative conceptually. Again,
hmm
I joke that the most straightforward answer to this question is to just say it's just tiny black holes from the Big Bang. What's more obvious? It's not obvious. I'm teasing. But it requires making no new particles. It requires not changing the laws of gravity as we know and love them and test them. And it then requires us to chase that, hypothesis down. How would we know? What would it
It's
look like?
Occam's razor of this case.
Yeah, I think it has some merits on that score. And so we can ask for how would they form? We have better and better ideas about that based on our understanding otherwise of the conditions around the Big Bang. What should we look for? Maybe something like a Mars wobble or very subtle effects from something called Hawking radiation, which, again, something in my own group and others work a lot on. Could we really detect that with current technology? I think we probably could. Would it show up in other deviations from other ways that dark matter might behave on large scales? We don't know. There's lots of questions to pursue. And it might even be right. But even if it's not right, we're going to learn a lot. And it goes back to these, if it's mistaken, hopefully it's a really productive mistake. If it gives us clues for the next big thing, that's pretty great too.
That's awesome. That is, I have to say, freaking awesome. And Dr. Kaiser, I want to thank you so much for your time. I would love to have you back at some point because I really this has been a real ball for me. This has been a real treat. And thank you for being so eloquent and generous with your time and for really doing such an awesome job taking these complicated and really difficult ideas and helping make them digestible. I hope that everyone listening enjoys it as much as I did because this is really just such a blast. Thank you.
I appreciate it. It's fun for me, and I'm glad to be able to talk about it with you. And I appreciate the invitation.
Yes, I'm a big fan and I hope to have you back soon. Thank you so much.
Thanks so much. Yeah. Bye bye.